Everyone, so I'm going to go through some examples of different types of series and what tests I would use and how I'm looking at them. Okay, so what I'm going to do is write a bunch of different series out on the screen. You can pause it, try for yourself, see how you would approach the different ones, and then check to see if you do the same thing that I did. Now, some approaches will work the same as others, but in general, this is how I'm seeing them. So first, I'm going to write out the different examples, and then we'll go through them. Right, so first n to the third, or n cubed divided by n to the fifth plus 3. The second is the sum from 1 to infinity of 3 to the n power divided by 4 to the n power plus 4. Okay, the next one is the sum from 1 to infinity of n factorial times n plus 1 factorial divided by 3n factorial. Okay, so 4, we got the sum from 1 to infinity of negative 1 to the n power times cosine of 1 over n. Okay, the fifth one is 0 to infinity of n cubed times x to the 3n divided by n to the fourth plus 1. Right, so there's an x in this one, that's just a different variable. You'll see more of that in the next unit. Okay, next one is going to be the sum from 1 to infinity of n plus 5 divided by n times the square root of n plus 3. Okay, and then let's do 2 more. So I have the sum from 0 to infinity of negative 1 to the n power divided by the square root of n squared plus 5. Last one is 1 to infinity of negative 1 to the n power times n factorial over pi to the n power. Okay, so one complaint I got was that a lot of the problems I do are too easy, so hopefully those are not too easy for you. At this point, you can pause the video and attempt just to see what test you would use on your own first, and then we can come back to it. Okay? So hopefully you attempted 1 through 8, at least gave it a shot. So this is what I see when I look at some of these right here. Okay, so again, the first thing you're always going to try to do is the nth term test. So right here, if I do the nth term test, my bottom is bigger. I got 0. That tells me nothing. I do notice, however, that this is relatively simple. Okay, I don't want to integrate this or anything. It's definitely not a p-series or geometric or anything like that. But if I get rid of this 3, so if I ignore this 3 right here, then I essentially just have n cubed divided by n to the fifth, which simplifies to 1 over n squared, which is a p-series. And I know that this is convergent. So on number 1, I would use the comparison test. You could use the limit comparison test if you want to be a little extra, but you could just use the direct comparison test. Compare to 1 over n squared, a p-series, which is convergent. Okay? Okay, so on the second one, kind of depends on how you want to go about it. So, okay, so this is kind of tricky. Now, I see these exponents right here, so you could do the root test. Okay, I think the root test would totally work. You could do the ratio test. I think the ratio test would totally work. What I see when I look at this is I see two numbers with the same exponent and some constant. So again, if I ignore the constant, then let's consider what I have here. So if I ignore the constant, okay, so a lot of times if you just have one or two lingering constants in the numerator denominator, you just ignore those for a second and see what you have. In this case, if I ignore that plus 4, I end up with 3/4 to the n power because my power on top and bottom was the same. This is a geometric sequence, or sorry, this is a geometric series that does converge because 3/4 is less than 1. So I can compare to 3/4 to the n power, and which is convergent. That's a good thing. And so in this case, I would just do another comparison test. However, if you did the root test or the ratio test, I couldn't blame you on that. I think it would take a little longer, but that's totally fine. It should work to get you the same thing. Okay, on number 3, I see a bunch of factorials. So my first thought really is going to be the ratio test. Okay, my first thought's usually going to be the ratio test on this. So remember that you're going to substitute n plus 1 and then divide by your given, or basically multiply by the reciprocal, and ideally a lot of things will cancel. Just keep in mind that when you substitute n plus 1, you'll end up getting something like this. N plus 1 factorial is the same thing as n plus 1 times n minus 1, and so forth, times n minus 2. And so at any point, you can stop this train here, you can stop it and write, okay, well, it's the same thing as n plus 1 times n times everything else. So same thing as n plus 1 times n factorial. And the reason why you would do that is so that you can cancel out different factorials, okay, top and bottom, to get them to match. So I would use the ratio test here, just because there's pretty much every time I see a factorial, like here, or whatever, I think to use the ratio test. Okay, next one. So here, the nth term test does work. The nth term test does work. So if you evaluate the absolute value of this, um, as n approaches infinity, you'll get cosine of 0, which is 1, which is not 0, obviously. And so it does diverge by the nth term test, so not too bad there. Okay, here I have a bunch of exponents going on, and I even have a different variable, so this is a good example of when to use the ratio test. And again, a lot of things should cancel. A lot of things should cancel. And we actually like this situation because we can use our exponent rule. So remember, if, for instance, I have x to the 3n plus 1, which is the same thing as x to the 3n plus 3, then because my exponents are adding here, that's the same thing as this. I can split apart my base. Okay, so remember that you can do that so that you can cancel different things. Okay, so next one, number 6. Okay, so basically, again, like I said over here, if you just have one or two constants, just ignore those and see what you have. So if I ignore my constants, I'll end up with, so I'm going to erase some of this stuff. So if I ignore my constants, I end up with n over n square root of n. Boom, boom. Okay. So that's what I see when I'm doing these series. If there aren't a lot of constants happening, so for instance, like number 5, a little more complicated, a lot of stuff happening. Okay, number 3, factorials, bad stuff. Number 4, I have a trig functions, totally different. Actually, I didn't even have to get to that point because I could do the nth term test. But like on number 2, number 1, number 6, they're relatively simple, not a whole lot's going on, and I have one or two constants that are being added or subtracted. In those cases, just ignore the constants and see what happens. And in this case, I end up getting just 1 over the square root of n. This is a good candidate to compare to, right? So I can compare to 1 over the square root of n, which I know this diverges because it's a p-series where p is 1/2, which is less than 1. Okay, so this is a good candidate for the comparison test. You could do the limit comparison test as well. I think the limit comparison test is best to use when you have different kinds of functions going on. So in this case, I have linear and square root, so you could totally use the limit comparison test in this situation. I would definitely use the limit comparison test if I have totally different types of functions happening. Like if I had, for instance, if there was like an n right here, so I had 4 to the n plus 4n, that would be a case where if you wanted to pick something to compare to, I would not do a direct comparison test. I would do the limit comparison test there. But honestly, that's another story. Um, you're not going to get something that's that weird without some other method of doing it, like the ratio test or something like that. Okay, so we're almost done here. Um, okay, so number 7, I have an alternating series. And so this is going to, okay, so when I see that, when I look at this, again, I kind of ignore this plus 5, and I see that I have negative 1 to the n divided by the square root of n squared, which is just going to be n, essentially. So I would expect this to behave similarly to the alternating harmonic series. Yeah, I would expect it to behave similarly. That's what I'm looking at when I see this. And so, because it's alternating, you just go about your alternating series test. So make sure that your terms are alternating in sign, decreasing in magnitude, and the limit of the absolute value of the limit to infinity approaches 0, which it does. So this will converge, and like I said, I would expect it to because I would expect it to behave like the alternating harmonic series. Now, if I asked you if it converged absolutely, you take the absolute value of this, and again, because I would expect this to behave like the alternating harmonic, I would expect the absolute value of this to behave like the harmonic series, which is divergent. So I would not expect this to converge absolutely. I would expect it to converge conditionally, and you could go through the check on that yourself. But that's the way I'll go about this. So it should behave like the alternating harmonic series. So I would expect it to converge, but I would not use that as reasoning. I would do the alternating series test, just to be clear. Um, I'll do the alternating series test because it's alternating, so that's what you want to use here. It's just as an expectation, I would expect it to behave like the alternating harmonic because it's similar, and I would expect the absolute value of this to behave like the regular harmonic series, which it does. So this function is conditionally convergent. Okay, and then last one, I have a factorial, so I'm going to want to use the ratio test. Although, yeah, although if you do the nth term test, you also get infinity. So the nth term test should work here. Factorials increase faster than exponentials, so the nth term test should work. But if you weren't sure on that, so if you didn't remember the order of your transcendental functions, you could totally use the ratio test here. It should still work, and you should still get that the function is divergent. Okay, so hopefully these were better examples. I was asked to do some more challenging ones, so I think this was a good list of slightly more difficult problems. If you have any more questions over any of these functions, or you need to see how it's worked out or something, just shoot me a remind later or an email. Otherwise, good luck studying. See you guys later.